First of all, I have to thank all the organizers of this, like the astronomy club, for giving me the opportunity to represent my. This is actually my one of the work, so I'll be talking about that. Okay. So yeah, picture of that matter is also very important. So if you have any questions, you may ask at the end, maybe also. So let's start. So this is the brief overview of my talk. So um, you can't see the then it will be better if it's can you all see this for yeah. Yes. Also live on YouTube. So it's going to be overview of my talk. So production and the motivation why we are studying the dark matter panels and the things and the structure of dark matter panels. So, so that's the third point is that I'm considering them as an ellipsoid or beyond spherical this, and why I'm considering this. Then I will be discussing some parameters which used to describe this ellipsoidal shape, and I am looking at the distribution and their evolution. And then I am further classifying these ellipsoidal values into three categories: evolution, separately, and then the echo passage. Okay. So yeah, so this is the first slide. What it tells us, so we all have our budget in our entire life, right? So like so our universe was also energy budget, and it consists of dark energy, which is the dominant component of our universe, and it's massive dominating state point 3%. And this dark energy, which we don't know much about this dark energy, the only thing we know is it is the component which is responsible for directing nature of our universe. And then the other component is the matter that is divided into two parts. One is visible matter, which is we are all made up of that, with ordinary visible matter, and the rest one is the dark matter, which we also don't know much about that. So, and which is also the dominant component for the whatever the structure we see, not see, whatever the structure in the large scale will work, it is dominated by the right. So yeah, so since I am talking about the dark matter, so and I am talking about cosmological simulation. So basically, in cosmological numerical simulations, we are doing actually we need some prescription to simulate a particle. So pollution is dark matter. That is called cold dark matter. And this cold dark matter has been first, the idea has been proposed by the Gibbon and where the time with just 2 days ago. And he is just he didn't best known for his cold dark matter. Okay. So yes, so what we find in observation, we find only galaxies, right? So, but there is no direct observation of dark matter. But we have cosmological surveys by which we have seen. So, those who don't know about the is or you must have heard that our space-time is not yet completely flat. So it is a fabric. So when there is a massive object on the space-time, it gets stuck, and light also bends follows that one. So using that concept, there are detection of dark matter and how much mass contained in that curved space. one can estimate by the reflection angle. So, so we don't have direct detection, but the cosmological survey we can see, as I said. So from that, people have discovered that in 2004, two massive galaxy clusters they are coming close to Mars. Okay, and keep gas and dust particle, and this gas has temperature, pressure. So when they come together, so due to the drag force, their velocity gets dragged. So you have any pointer? No. Pointer no. Yes. Okay. So you can choose now. So this is the gas component. So they get dragged down due to the pressure. Okay. But what they have found that in this region there is enormous amount of mass there using that Einstein's theory. They have found that enormous amount of mass is there, but they can't see at all. So then they confirm that okay, this may be one of the matter which we don't see, but interact only through gravity, but there is no interaction to gas particle or dust. Okay. So this also gives us one confirmation that indirect confirmation that so there is something another matter exists. So this I have just drawn an analogy with the pond and so what is this? So if you have a pond with crystal water and there are some pebbles on it, so you can't see exactly the water because water is very clear. But if a wind is just blown on it, so you will see that it causes some it introduces some difference and that distorts the shape of this pebble. Okay. So here, this clean water is like a dark matter which you don't see. But when light passes passive object, like this, pupils are like the gas. So they what is happening? So the like what they are like waited here. So this is like one kind of analogy, one picture. And another point is galaxy rotation curve. So our galaxy contains stars and gas and dust particles. So if you use just Newtonian gravity and you easily estimate that you will reach the root of Gm by r. So as you go distant from the galaxy, the rotational velocity gets few just consider only stars and gas particles. But what we have observed, you can see this red line, which shows that there is some extra amount of matter which is present. That's why we are not getting if you use only star and gas. So this also another indication that there must be some unknown matter exists. Okay. So now we have got to know that observation suggesting the existence of this unknown matter, but we still don't know what is the true nature of it yet. But numerical simulations in the last 2 decades unprecedented job. So what and it producing realistic galaxies. Like you can see one of the galaxies from like so this is the gas density and the colored by temperature. So the density and temperature both are color coded. So this is like a 2D color map. And here these are like star particles. So you can see that some spiral kind of structure here. And the red dots are black. So it has also that's symbolic. So yes. So in numerical simulation, what we have found that these dark matters are playing the role of skeleton of the structure within which galaxies are situated. So this is one cosmological structure from cosmological simulation. And if you zoom in this here, to get this, and if you further zoom in, you can see one massive dark matter halo structure. Okay. So, and within which, so if this is like 200 kbc in size, and the galaxy size will be around 20 kbc. So,
What
what
is
is it?
KBC?
Yeah,
What is KBC?
kilo percent.
Kilo.
1% is 3.26 light year.
Oh, acha, KPC.
So, here, uh, here we can, showing one video which will show the evolution of a massive dark matter halo structure, how it evolved. Yeah, one of the undergrad student here. Uh, So you can see it starts with a very smooth structure. Okay, it's like a grid, right? But still there are some fluctuation is there, meaning, and that leads to gravitational instability. And over the period of time, this gravitational instability grows, and you can see a lot of small clumps form, and they merge together, and ultimately they form a very larger halo. And all these small structures, these are like segments. Okay? So from numerical simulations, how to identify these dark matter halos? Halos are like bound structures, right? So there is a phase space algorithm called Rockstar. It is focused over density calculation using phase space topologically adaptive refinement, which uses the particle position and velocity information and identifies the structure. Okay. So this is one kind of example, with a very massive halo, and you can see. So there are central halo, meaning the most massive halo is called central halo, and the small clumps is called satellite. So this is the halo boundary, okay, considering all the particles, and if we consider only the central halo, meaning the most massive one, the green one. So then, so this, when we talk about the structure of dark matter halos, so we are saying that it is not a spherical thing. It is an ellipsoid. Why we are saying this? You can see from this abundance of what is abundance of halos. Saying that the number density per unit logarithmic must be in the universe. Okay, number density of this halo per unit logarithmic mean. So the data points are coming from simulations, using simulation data, and these solid lines are from some analytical theory. Sector, sector. You can see that this data points matching very pretty well with this cyan line, which actually this sector will not function assuming this dark matter halo, the collapse of dark matter halo is to be ellipsoidal. Okay. So, what I have done, I have shown here a typical picture of a halo and how one can compute its shape. So it is not a spherical thing, right? So you can compute its shape using a tensor, shape tensor, and you can we define this ellipsoid by these three axes A, B, C. Like ellipse, you have A and B. Okay, and the three eigenvector A, B, E, C. And the three triaxial parameter is Q, which is the by A, medial to largest axis, and S is C by A, shortest to largest axis. And P is called the triaxial fraction. So my main one are just looking at the distribution of this Q and S parameter and how it works over the period of time. Okay. So yeah, this is the first figure. So it shows this Q and S, these axis ratios across different simulations, and this it has been plotted as a function of mu. So mu you can think of like function of mass and cosmological time. So what it shows, so the low mass halos are more spherical, when Q is very meaning when Q is tending to one, it is like a spherical object. As Q decreases, means it is going below, meaning it is deviating more and more of pericity, right? So low mass halos are more spherical and compared to this high mass. Okay. So and this spread is showing the one sigma distribution. Okay. So now I further classify these halos into three categories: oblate, prolate, and triaxial. And based on the triaxiality parameter which I have described here, is T. Okay. So when T is 0 to 1 third, I am saying it is an oblate. It's a very square thing. Okay. And prolate is the elongated one, and the triaxial is in between. Okay. So and then I have seen their uh, uh, structural evolution again. So they follow what I found that this Q and S across cosmological time they follow on a single path separately, universally. Okay. So and then what see this how these oblate triaxial and prolate fractions are evolving with times. Okay. So what you can see here, so this region is redshift, low redshift. Low redshift meaning just near computing. Okay. So what you can see that the prolate fractions are decreasing, whereas the triaxial and oblate fractions are increasing. Okay. So which is also consistent. Something is decreasing, that's why the other two are increasing. Okay. And then what we have seen that in this plot, what we have seen that how these axis ratios Q and A, okay, uh, they are evolving for a given mass range. Okay, how this contour of this axis ratio that they evolve from prolate to from prolate and towards the triaxial and then oblate across the red cell. Okay. So yes, and then yeah, these are the take home mathematics. So we have seen that distribution of and evolution of velocity they follow a universal path when we are plotting as a function of the and classifying them in three categories. They also follow a universal path separately. And the last point we find there is a morphological shift from prolateness and they evolve towards oblate and triaxial and oblate, right? You can see there is systematic shift in the morphological system. Okay, that's all.